All right, if I may, let's start. Welcome to YSoft, to Technology Hour Meetup. How many of you are here for the first time today? Okay, that's a lot. Thank you that you made it today. I know it's 6 p.m. Thursday. I'm exhausted after 2 days of software architecture brainstorming meeting, so you can imagine it was pretty exhaustive. So thank you that you made it. Today it's my pleasure to introduce you Mark Seemann, who's a developer, author, teacher, mentor, software, and anything actually. Today he will be talking about equivalence classes, and I will leave to him so that he explains what it is. After the talk, please don't leave. We will move to relax room where there will be a lot to eat and drink and discuss. So thank you for now, and I'll pass the word to Mark.
Thank you. All right, so good to see all of you. Thank you all for coming. It's I did a tweet 20 minutes ago where the seats were completely empty. So I was hoping that more people showed up, and luckily you did. So thank you very much. And I also want to thank Jakob for actually inviting me here. It's been like 25 years since I was last in Prague, so that's kind of a bit of time. And Jakob told me he's actually not 25 yet. So, but I don't know. It may not have been exactly 25. I don't know. But it's been a long time, so it's good to be back. Right. So I was told by Jakob that maybe some of you are not .NET developers. How many of you are .NET developers, or would term yourself .NET developers? Okay, great, lots of you. And someone who's not a .NET developer, please, a couple. Okay, that's fine. Don't leave though you're not .NET developers. What I'm going to say here today, I think, should be perfectly understandable for you, even though you're not .NET developers. And if you have questions, then just ask them and I'll try to explain them. But basically what I'm going to do on a technical level is going to be quite simple. I like to talk about conceptual things, so that's mostly what I'm going to do. But I'm going to show you lots of code. I'm going to write code and you're going to help me in 10 minutes. So get ready for that. If you're tired now, then just get ready to actually help me write some code in 10 minutes. Right, okay, so as you can tell, my name is Mark Seemann. If you have any sort of need for getting into contact with me, I should stay near the microphone, by the way. If you have need to contact me, there's lots of contact information there on the blog, that link there. Also, Twitter is kind of my favorite feedback mechanism. So if you like the talk, you can tweet it, after or during. If you don't like the talk, well, you can do something else, I don't know, or still tweet it. I mean, it's up to you, obviously. But that's basically it. So today I'm going to talk about equivalence classes mostly. So I know there's lots of things in this title. It's a horrible title, but I'm mostly going to talk about this thing called equivalence classes. And if you don't know what an equivalence class is, that's great, because that's why you're here. You're here to learn about what's an equivalence class. And then there are some technical things that's not really very interesting. And then we have this thing called property-based testing, which is also extremely exciting. And I'm going to talk a little bit about that later on today. So about like maybe 30 minutes into the talk, I'll start talking about property-based testing. But from the beginning off, I'm mostly going to talk about equivalence classes, because I think it's an important thing to understand what's an equivalence class before you understand what property-based testing is. All right, so so that's basically the words. So I'm going to talk for about an hour, and I'll do live coding as we go along, and then we'll have the break, and you can ask questions, and we can relax and have fun. All right, so first of all, what's an equivalence class? So the first thing I need to tell you is if you come from a background where you do C# development or Java development or maybe C++ development, you know what classes are. Okay, equivalence classes are not that kind of classes at all. It has nothing to do with object-oriented classes. Equivalence classes is like a category, it's like a set, it's that kind of a class. Okay? So it has nothing to do with object-oriented code. So today we're going to talk about F#, which is a functional language, but actually the concept of an equivalence class is it's not tied into functional. You can think about equivalence classes in functional programming, in object-oriented programming, and whatever sort of programming you can. And also, now I said F#. All the code I'm going to show you here today is F#. If you haven't seen F# before, don't worry. I'll only show you very basic F#, and I think you will be able to follow along even if you have never seen F# before. It's just a very nice language, though. So that's basically it. So what's an equivalence class? Okay, let's have a look at the definition. So it's a test condition identification technique that is used to reduce the number of tests required by grouping inputs that should result in the same output or which should exercise the exact same logic in the system. How about that? Now, that's all I have to tell you. Now you're much smarter. Thank you. No, obviously not. Well, that's quite a mouthful, right? That may not actually make you smarter. This is a quote from an otherwise great book that's called X-Unit Test Patterns, and it's a book that I really recommend that you read. And most of the book is not like this. Actually, most of the book is quite readable. But this is not, I admit. And I kind of took it just because that was it's actually one of the more concise definitions I could find, but it's not particularly helpful, right? So I was in this lucky situation that when I first encountered this thing, I was reading that book, I think I read it in 2007 or 8, something like that. And I was lucky enough at that time to be traveling, and back then you didn't have ready access to the internet all the time. So I was reading this book while I was traveling. I was on a plane or a train or whatever, and some sometimes this concept came up in the book, not that many times, but he said, well, an equivalence class that, an equivalence class this. And I was like, he never really introduced what's an equivalence class. So I looked it up in the index and I found it in the glossary. So there's this glossary in the book, and this was what it had to say about it. That was it. Now, and because I was traveling, I had too much time and I didn't have any internet access at the time. So I had lots of time, too much time. So I began to think about that. And after, thinking about it for a long time, like 15 minutes or something like that, it began to dawn on me what was actually meant by this. So we could spend the next 15 minutes just doing a very word-by-word analysis of this, but that's going to, if you're not bored yet, you will be. So let's not do that. So instead, I want to show you by an example and try to explain to you what an equivalence class is. But if I should just distill what it is, it's a test technique. It kind of says that already, but it's a technique to identify which input values that you should use for test cases that are equivalent to each other, that should provoke the same behavior in your system under test. So that's another way to put it, but let's look at examples instead. All right, so first of all, I'm going to use some technologies to show you the example. That's actually not very important, but let's just do that very quickly though. I'm going to use something called xunit.net, which is an open source unit testing framework for .NET. It's in my opinion the best unit testing framework we have in .NET currently. If you're not familiar with the xunit.net, but if you know different things like NUnit or MS Test, or if you're on the Java platform, you know JUnit, or maybe you work with Jasmine in JavaScript, it's kind of like the same thing. It's just a unit testing framework with a test runner. And then I'm going to use something called Unquote, which is just a very little assertion library, and I'll show you why that is cool, so I'll not spend more time on that right now. And then later on, I'll use something called FsCheck, which is this property-based testing framework that we can start using later on when we start talking about what is property-based testing. But for the next 30 minutes or so, I'm not going to talk about that, but I'll introduce that when we get to that. But those are basically the technology stack that I'm going to use. Right, so what I'm going to do here is I'm going to do test-driven development. And if you've ever heard about test-driven development, hopefully you've heard about this red-green refactor cycle. Basically says, well, the first thing we do is we write a failing test. And since we're working with a statically typed language, F# is a statically typed language, it means that often what we do first is that we write a test that doesn't even compile. So this is like, there are actually two sub-phases of this phase. First we write a test, and it doesn't compile, and then we do enough in order to actually make it compile, and then we run the test to see that it actually fails as we expect it to fail. So that's the red phase of it. Then we use the green phase where we say, well, we just write enough code in order to make that test and all the other tests pass. So Ken Beck says, you're allowed to commit all sorts of sins against proper software development in this phase. The only purpose of this phase is just to make the test pass. And then the third phase, then now you can look at the horrible code you just added in the green phase and say, well, that looks really horrible, let's make it nice. So now you can refactor. So you change the implementation, but you don't change the behavior of the system, and then you can start all over again. But I'm going to throw a little wrench into the system because I'm going to use a technique called devil's advocate. And the devil's advocate technique is a technique that I sometimes find useful. What it does is basically it says, well, in the green phase, the idea in the green phase is that we should do the simplest thing that could possibly work. But sometimes, the simplest thing, it's not, it's subjective. What's actually simplest may not be, what's simplest to me may not be the same that the simplest thing for you. So how do you actually know what the simplest thing that could possibly work is? And if you're in doubt, what the devil's advocate technique says is that we should always do the wrongest thing we can do. And the reason for that is if we pick the solution that is obviously wrong and we still have all green tests, it means that we should write more tests. So the devil's advocate technique is a way to figure out, when do I have enough test cases? Because as soon as I can't really come up with a good wrong solution that passes all my tests, I probably have enough test cases. So this is a way that I can use to figure out when do I have enough test cases and when do I not have too many test cases. So that's kind of an interesting way to do it. And I'll do that in a couple of minutes. But let's see. I'm slowly approaching the problem, and I'm going to switch to actually writing some code very soon. But first of all, we need to now know what sort of problem should we solve. So I'm going to solve this thing called the FsCheck Carter, and you've probably heard about this. And I know it's a toy problem, I'm going to show you just what the rules of this is. But I know it's not a real programming problem, but on the other hand, it has this advantage that it's actually something that we could do in 20 minutes, which we can't do with a real problem. So yeah, we'll have to make use with something we can actually do in the time given us. So the FsCheck Carter, for those of you who don't know it, basically you have to write a program that prints the numbers from 1 to 100. But there are special cases. If the number is a multiple of 3, we should print fis instead of the number. And if it's a multiple of 5, we should print bus. But if it's a multiple of both 3 and 5, we should print fis bus. That's the rules. So that's not particularly complicated. And actually what I'm going to do is I'm going to narrow it down even further, because I think the thing from 1 to 100 is actually pretty trivial to do. The difficult part, if you will, is having a function that takes an integer's input and produces a string as output according to these rules. And believe it or not, there are actually people who call themselves professional programmers who cannot solve this problem. I've never met them myself, fortunately, but I've heard enough anecdotes about it where people use this thing as a screening technique for, when they want to hire new candidates. And people report that they throw away lots of people because they cannot solve this problem in reasonable time. That's kind of scary, but that's actually the case. Okay, so I'll try to write, using test-driven development, a function that can transform an integer to a string according to these rules. Okay, so that's basically what we're going to do. So that shouldn't be too hard, right? Right. So I'm going to switch to Visual Studio. So for those of you who are not .NET developers, that's just the IDE that we use. Is this readable from the back, or do I need to make the font bigger? Or a little. Some people say thumbs up. Some say a little bigger. Let's just do it a little bit bigger. Fonts. So we can do something like we can do 14. So that should really be enough. How's that? All right. Okay. Cool. So what I have here is I've just prepared the solution so that we don't have to spend time on that. So basically I've written no code yet, but I have this. I have my package manager here. It's something called NuGet, and I can just show you if I do get package. I have the technologies, the packages that I talked about before, XUnit and Unquote and so on. I'll talk about them as we go along, but that's basically what I have. And then I have two modules here, and modules are just, in F#, those are just ways to structure code, and you can put modules in the same file as I have here, you can put them in different files on different libraries and so on. To make things simple here, I'm just having them in the same file. So I have my module called FsBus, where I want to put my implementation, that doesn't exist at the moment, and I have my tests where I want to put my tests. So according to test-driven development, I should write the test first. So what I want to do is I want to write a test for the case where the number should just be transformed to a string. So no fizzing or no buzzing, just the number itself. So one of the nice things about xunit.net is that it doesn't require me to have classes with members and so on. I can just write functions and modules, and that's nice. So I can write a function, and I can call the function something. So let's call it FsBus.transform. So that's the one that's the thing that I want to test. So that's just the name of the thing that I want to test, and I say that my test case is that it should return the number. And you will notice one thing, I have these strange double backticks, and that's an F# feature that allows me to give a function a name with spaces in them. So the name of this function, if we just do this, now this is a complete function, doesn't do anything at the moment, but this is actually a complete function. As we can see here, I don't know if that's readable from the back, but basically it says it's a function that has the name FsBus.transform, returns the number, even with spaces and all. And it's a function that takes, at the moment, it takes something called unit as input and returns unit as output. And unit is written like this. It's the open and close empty brackets there. Unit is kind of an interesting type in F# because if you've used to C# or Java, you know the keyword void. So void is a return type in C#, for example. I think, is that the case in Java as well? Void, does that make sense? Or maybe it's called something else in void. Some people are nodding and the rest of you are sleeping already. All right. So, but the funny thing about F# is we have this thing called unit, and unit can serve as both an output type and an input type. And we just write, unit has one value and it's written like that. So that's unit. So basically if we want to translate it to something this is a function that returns void, but it returns unit. Same thing. It compiles to void actually. So that's pretty nice. So here's a function which with a strange name with spaces in and all, but that's just nice when we write tests that we can actually give the tests a nice name and don't have to deal with underscores and all sorts of ugly things. So let's try to write the test. And it's not going to compile at first, but let's try to write it anyway. So we need an actual value. That's going to be the result of the calculation. So I want to call the FsBus module, and I want to call a function called transform in that module. It doesn't exist at the moment. And I want to pass in a number. That number here is also a value that doesn't exist at the moment. So this symbol doesn't exist right now. But I'm trying to first write my test as I would like it to look like, and then we'll make it compile afterwards. So actually we can say something like, we need to define what is actually going to be. I want it to be a string. So typically we don't do type annotations that much in F#, but we can in order to force the compiler into doing certain things if we need to. What do we expect? Well, expected. So my expected result is the string value of the number. So string here is a built-in function in F# that basically just returns the string representation of any value, not just numbers, but anything. And the reason why we can't do that is on .NET, everything derives from object, and object has a toString method on it. So the string function just calls that behind the scenes. So we can always, convert any object or any value into a string. Sometimes it's not very informative because it's just the name of the type, but for numbers we actually do get the string representation of the number. And now we need to write a verification that we say that actual is actually equal to expected. And I can use unquote for that. So I say test. Test is a function that is defined in this unquote library. It's just an assertion library, and it enables me to write tests verifications like this. So I'll do this, and I'll write expected equals actual. And that looks a little bit strange, but I'll talk about what that is. So if you forget those strange delimiters for a moment, what you have in here, expected equals actual, this is a Boolean expression. It's not an assignment. The equal sign is an equality comparison. And the reason for that is normally you would be used to in C# or maybe also in Java, you would have double equal signs if you want to do an equal to comparison. But in F# it doesn't work like that because it's not ambiguous. We don't really do assignments that much in F#. This up here, for example, this equal sign here is not an evaluation and it's not an assignment either. It's something called a binding, and the reason why we can unambiguously say that is because of that let keyword. So if the let keyword appears in front of us, it's a binding. We're actually taking the value and bind it to that symbol. But in this case, we don't have any let symbol, so that this is actually an equality comparison. We're comparing is expected equal to actual. So what about those strange delimiters here? Well, this is something F# has which is called a quoted expression. You can think about it a little bit as a lambda expression. What it means is it's an expression of a Boolean expression, but it's not just the result of doing the Boolean expression. It's actually the expression itself. So it's an expression tree, and we sort of pass the expression tree to this test function here. So not only can it evaluate that Boolean expression, but it can also look and understand what was the Boolean expression. And it's going to be apparent why that's interesting in just 5 minutes, maybe 2 minutes. Anyway, but this is basically what I want my test to look like. It doesn't compile at the moment. You can see we have red squiggly lines under that transform thing here. So at the very least, I need to define a transform function in my FsBus module. So I can say let transform of number be something that returns a string. So this is a function that returns a string. Actually, this is a function that takes an argument called number, but right now it's a generic type. It can be anything. So the type inference system in F# just says, well, the number is not used, so it could be anything. Later on we will constrain it, but for now it's not really used, so it could be anything, including numbers, but it could be anything. So now it doesn't compile because we've never defined what number is. So what I could do something like I could say let number equal blah 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 whatever, but I'm going to do this a lot of times, so I'd rather want to do a thing called a parameterized test, which is something that xunit.net allows me to do. So I can say let's declare that this function should take a function argument, which is the number, and then I can call that function multiple times with different numbers. So this actually compiles. Now if I try to run the test right now, nothing will happen because I need to do a little bit of annotation, but I can prove it to you. Now I'm trying to run the tests, and if I just pop up my test results, you can see nothing really happened. There are no results, no tests were actually run at this point. And the reason for that is that I need to decorate or annotate the function a little bit, and I can do various things, but what I want to do is use something called a theory, and a theory goes together with something called an inline data, and I can have many inline datas, but I was just going to start with one. And basically what I can do is I can pass a value here, and that value is then going to be passed as the number when the test runner runs this function. So I want to test this, and this is where you're going to help me. Now, which number should I use? -1. All right, okay, that's fine. Let's do that. Actually, if we think about the problem description of the FsBus kata, we should print the numbers from 1 to 100. So you're actually outside the bounds of the problem description. But I'm okay with that. We can widen the bounds. It's not going to be a problem. I agree that -1 should also produce the number itself. All right, so if we run the test now, we should expect the test to fail. So let's see if that happens. And it does. It pops up here. I hope you can read this. And it says 0 passed and 1 failed. And if I just press enter, we can see where it actually failed. So it wasn't an exception. It was actually, it threw an exception in that test function here, which is what's supposed to happen. I'm just going to pop this up again. So what this thing unquote does is it actually takes my Boolean expression, but instead of being an abstract Boolean expression with expected equals actual, it plugs in the actual values. So it says, well, the Boolean expression before it was evaluated was that the string -1 should be equal to the empty string. And then afterwards, it tells me that evaluates to false. That's quite clear to us, but it just does that step by step. So in this case, maybe unquote is not that helpful, but if you have a more complicated Boolean expression here, what unquote is actually going to do is it's going to evaluate it stepwise and plug in the values and say, and that part of the Boolean expression actually evaluates to false, and then when you evaluate that together with the other part here, then that evaluates to whatever and so on. So you can actually see how it arrives at the conclusion that the test is not passing. So instead of having to learn lots of different, assertion libraries and having to write all sorts of, manual tests, failure messages and so on, you can just let Uncode do that for you automatically. So that's very nice. But anyway, that's just a little bit of an aside. So what's the simplest thing that can make this test pass? I can pretty much do this, and that's going to make the test pass, right? Okay, I'm just going to hard code -1. And if I pop up the result, you can see it says 1 passed and 0 failed, right here. All right, so that's fine. We didn't expect to arrive at a complete solution in one step, I hope. So we need more test data, apparently. So I can copy this and I can take another value. So which one should I pick now? Can I get another suggestion?
4.
4. Okay, we'll do 4. I agree, 4 is a valid test case here. So when I run the test now, we can see it says 1 passed and 1 failed. And basically, again, it says, well, if we evaluate the string 4 to the string -1, those are not equal to each other, so that evaluates to false. That seems reasonable. So here's the thing about the devil's advocate technique. So maybe I would say now, what's the simplest thing that could possibly work that will make this pass? So, well, I could do this. That's pretty simple, right? But I'd rather err on the side of doing something that is deliberately wrong. Okay, so let's do this instead. Match number with, and we'll say, well, if the input is -1, we will output -1, and in all other cases, so this is just a catch-all thing, we'll output 4. All right, so this is something called pattern matching, where you just say, well, if the number is -4, this is going to be the result, and in all other cases, it's going to be -1 is going to be -1, otherwise it's going to be 4. And this actually passes all the tests. So if okay, my keyboard shortcuts just failed me. So this has 2 passing and 0 failed tests. Okay, so can you give me another one, please?
98.
98. Okay, 98. I trust you that it sounds like, yeah, that's not divisible by 3. Or 5. Okay, let's try to do that. So it says 2 passed and 0 failed. Okay, that's pretty much what we expected, so that's cool. So I could just keep on going like this. I could do, maybe we should just say, well, okay, so 4 is also a special case, it turns out, and we could say, well, the fallback thing now is that 98 is the rule. Now, we could do that. And at some time, after I've been doing this a couple of times, you get tired of that. Obviously, I mean, this is obviously not correct, but also now you're beginning to see, it looks like there's some sort of pattern here. -1, okay, 4, 4. It looks like there's a pattern. Maybe, even if I didn't know the rule, you're beginning to figure out, okay, I think I know what's going on here. Even if you didn't see the test, imagine that you didn't see the test that you just wrote. So at some point, I like to often have 3 test cases, and I say, well, if I have 3 test cases that demonstrate that something should work in a certain way, that's probably when I could start generalizing. There's this thing called the rule of 3. That's kind of where you can use that. So in this case, I'll say, well, now I have 3 test cases that kind of try to demonstrate the same thing. Maybe at this point, I can go to my refactoring phase and actually do this instead, and that should also pass all 3 tests. Okay, so it does. Right, so I'll go slow at the beginning and I'll speed up slowly. So I'll accelerate slowly and go a little bit faster every time. So normally when you do TDD, you should not do copy and pasting, as I just did. But I'm allowed to do that because I'm doing demos. So let's do the FIS thing. And in this case, the FIS test case is this. So no matter what the number is in this test case, the expected outcome should always be FIS. All right. So I need a test case for that.
6.
What? 6. All right. So we should expect that to fail. And it does. All right. So maybe I should just go back and say, let's do some pattern matching again. So, and we can say, all right, okay, if the input is 6, let's do FIS. And in all other cases, you can see where this is going, right? We'll just do the string of the number. Now, if you think about this as not just test-driven development, if you think about this in terms of the scientific method, you start sampling data and you're kind of trying to figure out, for this input data, what should the outcome actually be? You don't really have enough data to form a good hypothesis yet, because you just say, well, 6 should produce FIS, and it does. It actually passes the test. But you don't really have enough data to work with yet, so you need to throw more test data at it in order to establish some sort of hypothesis that you can test. Please, another number?
1,000,002.
It must be a Czech thing. 1,000,002. 1, 2, 3, 4, 5, 6. All right, are we good? So when I did this in London, Thomas Petricek was also sitting about where you were sitting right now and throwing, billion numbers at me, and I'm kind of like, okay, I had to count all the zeros, but I think this actually, there's this rule when you can do the, you can just sum all the ciphers, and if that, is divisible by 3, then the number is divisible by 3. So that's cool. This should not pass at the moment, and it does fail. But again, we can just go up here and I can say, notice how terse F# is. We can just do this. And that actually passes all the tests. So isn't F# a nice language? Right, okay, let's do another one. What do we want? 81. 81 is divisible by 3, yes? All right, let's do that. Okay, then that fails again, and you can see where this is going. If we do devil's advocate first, we can just do this, and that's actually going to pass all 6 tests. So I'm just going to pop those up. So it actually passes all 6 tests. But we should never forget the refactor phase of the red-green refactor cycle. So at this point, we may say, is there something that these 3 numbers have in common? Maybe it's not very clear at the moment. So if it was very unclear, we might need more test data. But on the other hand, we kind of know the rule. So we can say, well, these are all numbers that are multiples of 3. So how do we figure that out? We could do this. We could do modulo 3. So the modulo operation is just do an integer division and take the remainder of doing an integer division. And if that is 0, if the modulo operation is 0, modulo 3 operation is 0, then the outcome should be FIS. So that's my refactoring. So now the code looks nice again, and I have 6 passing tests. All right. So let's do copy and pasting again. You are not allowed to do that at your work, okay? But let's do the bus case. And I'll promise there's another one that we need to do as well. Oh, yeah, there was one that didn't have any value. So it kind of throws exceptions if you don't pass a value here. But can I get a good value for the bus test case? 55. All right. As you can see, I'm always running the test to see that the test case that I just wrote actually produces the failure. So again, if I wanted to do a devil's advocate, maybe I could say, well, let's not only match on the number modulo 3, but let's also match on the number itself. So by introducing this comma here, I'm actually creating a tuple of numbers, and a tuple is like it's a complex value that contains 2 elements. In this case, both elements of type integer, but they could be of other types as well. And I can say in the FIS case here, I'm saying, well, if the modulo 3 operation returns 0, I'll just do this underscore, which means I don't care about what the number itself was. But before that, so pattern matching F# goes from top down. Before that, I could say, well, I don't care about what the modulo operation was, but if the number itself was 55, was that the case? Was that the number? 55, yes, thank you. If that's the case, I can do bus, if I could spell. All right, okay. So in this pattern matching basically just says, well, no matter what the number modulo 3 is, if the number itself was 55, then it's going to be bus. Otherwise, it's going to fall down to the next one until it matches one of them. So that's 7 test cases that's passing. So again, this is not the correct implementation. That should be pretty clear to anyone. So so we need to throw more test data at this. Okay. Can you give me another one, please? 10? All right. Sounds reasonable. and that fails again, and you can see where this is going, right? Let's put this up a little bit. I'll just do, let's do this, and I'll just do like so. And that passes all my tests. So I promise that I'll speed up again in just a while, but let me just get the last one here. So another number, please. 0. So 0 should that produce bus? Is it a multiple of 3? Is it a multiple of 5? It's actually a multiple of all numbers. Or at least if you do a modular operation, you will get 0 as a remainder. So I don't agree that 0 is the correct number to use here, because it should produce FsBus.
75.
I'm sorry?
75?
75? That is also a multiple of both 3 and 5. So that doesn't work as well. Yeah. No, but it's good that you give me this number, because this allows us to actually discuss what is a valid input number here. And that's, we're not going for the FsBus case yet, but please do remember the suggestions, because we're getting to those in just a moment.
100.
100. All right. Yes, that's not a multiple of 3, so that sounds reasonable. Right. Okay. So that's a failing test. So let's go up and fix that. So again, I could do. Let's just do that instead of talking about it, and say, well, that's going to pass all my tests, and yeah, that passes all 9 tests that I have at the moment. But then I'll do some refactoring, and I'll say, well, I don't want to do it like this. Let me instead say, well, let's do a tuple of modulo 3 and modulo 5, and say, well, no matter what the modulo 3 operation was, if the modulo 5 operation was 0, I'll produce bus. Otherwise, I'll fall down and say, if the modulo 3 operation was 0, it doesn't matter what the modulo 5 operation was, and so on. So pattern matching is a pretty nice way of expressing this sort of problem, and that also passes all 9 tests. All right, so let's, if I could hit all the right keys, so let's do this a little faster now. So I only have one test function to write still, so this is the FsBus test case. All right, so let's just do all 3 at once here, because you kind of see the pattern here. So I already had some suggestions before. What someone said 0, right? And someone said 75. Can I give the third one?
1,000,005.
I'm sorry?
1,000,005.
1,000,005. Okay. I have to trust. Yeah, that sounds reasonable. 1, 2, 3, 4, 5, and then the 5. Does that look correct? Okay, thank you.
You're welcome.
All right, so we should expect to have three failing tests and 9 passing tests, and that's exactly what we have here at the moment. So we can just go back to the implementation, and to make a long story short, we can say, well, if both those modular operations are 0, we'll return FsBus. Okay, so this is the final implementation we have of the FsBus kata. And you can see now we have 12 passing tests and 0 failing tests. And then just to demonstrate to you, why did I say that the printing of the numbers themselves, from 1 to 100, why did I say that was trivial? Let's just have a look at that. And this may be a little bit difficult to see in the back. Let me see if I can get this a little bit further up. So this is the F# interactive. This is our REPL, our read eval print loop. And I just pushed the FsBus module down to that, so we can say we can take the numbers from 1 to 100, and F# has list comprehension, so we can just write it like that. This isn't that nice? And we can say list.map, and that just means every number here we map with the FsBus transform function. And this, I can never spell transform. But now we have the numbers from 1 to 100 printed in this way. So that was pretty trivial. So the hard part is actually to creating the transform function. I hope that's somewhat clear. All right. So that's the implementation. Now you could ask yourself some things. So if you've ever seen a live code demo before in a tech talk, you know that often it goes wrong for the presenter. Okay. Have you ever seen that? Presenter that wants to do live coding and it goes horrible wrong. So why do I take the chance? Now in this case, the problem is so simple that, unless my computer is crashing, I'm probably okay. But still, why do I make it extra difficult for myself by asking you of those numbers? Why did I ask you for those numbers? Why didn't I just come up with some myself? That would have been safer for me as a presenter, right? Because it doesn't matter. As long as you provide the numbers to me that have the correct qualities. In this case, you had to provide a number for me that was both a multiple of 3 and 5. It didn't matter which one it was. If you told me something, if you told me other numbers here, I could have done this instead. So instead of 0 here, I could have used 15, for example. It would have given the same result. It's just a question of how many numbers do you actually throw at the problem, not what are the numbers themselves. It's just that the number has to have, it has to fulfill certain properties. In this case, it has to be a multiple of both 3 and 5. So I just replace the number, that 0, with the number 15. And if I go up and comment out the implementation, the FsBus implementation, I should still have 3 failing tests, just like I had before. And it says down here, 9 passed, 3 failing tests. So the actual value here doesn't really matter. I could, instead of having those things, this is why I took the chance of asking you about those numbers, because there was no chance involved in it. I was perfectly safe all the time. So it doesn't really matter. I could, instead of saying 15 and 75 and 1 million and 5, I could just have said something like, maybe I could just said, 13 and 45. It would have amounted, it would have driven me towards the same implementation. These numbers are equivalent in this context. This is why we call them equivalence classes, because all the numbers that have these certain properties fall into the same set of numbers. They are all equivalent because they all drive towards the same behavior. Okay, so if that's the case, let me ask you about something else. How did you figure out how to arrive at those numbers? How did you arrive at 1 million and 5, for example?
The sum of the numbers.
Yeah. So you did the sum of the ciphers. Yeah, you can do that. But basically, what if you imagine? Could you imagine that if you just took some sort of seed, and I'll just write the seed here, and I'll say, well, if we had, if we started with the numbers 1, 2, and 3, is there a way, an algorithm we could apply where we could say, given 1, we could arrive at 15, and given 2, we could arrive at 30, and so on? Is that conceivable? I hope it is. How would you do this? So if I say, now if you imagine that instead of having 1, 2, 3, I'll do the replacement in a moment, but if you imagine that this number is actually 1, 2, and 3 instead of 15, let me put them up a little bit so you can see in the back. So instead of being 14, in just 5 minutes or 2 minutes, I'm going to replace those with 1, 2, and 3. How could you arrive at 15, 30, and 45 by doing some operation, doing some transformation of the number down here? How would you do that?
Multiply by 15.
Yes, you could multiply by 15, or actually I would like to say we could multiply by 3 and 5. I know it's the same, but it's just this is more like a domain-driven design-like thing. The Carter never talks about the number 15. It only talks about the numbers 3 and 5. So I think that's probably a little bit more in the language of the problem. But yeah, we could also multiply by 15. Yeah, so if we did that, we could take this 1 and we could just pass it in here, and then that would produce 15. And we could take that 2 and pass in here, and that would produce 30. And we could take this 3 here and pass it in here, and that would produce 45, okay? Does that make sense? That would, amount to the exact same thing. So we know now that no matter what we actually pass as seed input here, we always get the final numbers that fall into the equivalence class of being multiples of 3 and 5. But if that's the case, I could just bang on the keyboard and select some random number here, and I could run the test, and it wouldn't matter. Because now I've expressed how to transform any seed into something that falls into that equivalence class of being a number that is multiple of 3 and 5. And if you don't believe me, I can go and I can go and remove the FsBus case, and we should see that we have some failing test cases. In this case, three failing test cases. Right, so we still have the exact same coverage before. It wouldn't really have mattered. I could have done this from the beginning of, and that would have worked as well. All right, so we now understand that there's a way to arrive from any number to something that is appropriate for that test case. Can we do the same here? Could we do something when we say, well, what if I do 1, 2, and 3 here? Now, if I just do that without transforming the number down here, it would obviously fail because none of these are actually multiples of 5. So what can I do? Do any of you have a suggestion here? You are laughing now. It's a trick question, maybe?
Multiply by 5.
I'm sorry?
Multiply by 5.
Multiply by 5, yes. Is that always going to work? No. Actually, it's not going to, but I'm happy you suggested this. It's not going to, it's going to work with 1 and 2, but it's not going to work with 3 because that's going to be, that's going to be 15, which should produce FsBus. Yeah, so that's a little bit problematic. We could do something that's kind of like this. We could say, well, we could multiply by 3 and 5, because that will still give us a number that's always a multiple of 5. And then we could add another 5. That would still produce a number that's always a multiple of 5, but never of 3. Okay? Now, if some of you are a little bit uneasy about this, keep that in mind because I just made a mistake. And I'll tell you what that mistake is in 5 minutes. And if you know it already, I'll let you be cool and actually tell me what my mistake is. But I do know. So don't spoil it for the other people if you already see what the mistake is. But we can do this, and this should still pass. So we have 12 passing tests and 0 failing tests. And again, we can just verify that is actually true. If I comment out the bus, I should have 3 failing tests. And I do have 3 failing tests now. So we still have the coverage. It seems like we could go from any seed number to something that falls in the equivalence class of being a multiple of 5 but not of 3. Okay? So that seems reasonable. Can we do the same here? Yes, obviously you can. I think you can probably... What should I do here? I'm not going to write until you tell me.
Multiply by 3 and 5 plus 3.
Thank you. That's right. Yeah, so that will guarantee that I have a number that is a multiple of 3, but not a 5. And I could change these things to 1, 2, and 3, but it doesn't really matter because no matter what the seed is, I do arrive unless I have overflows. Sometimes when I do this, I actually have integer overflows but with millions, it's okay. So that still works. I have 12 passing tests, and we can do the same thing here in just the where it returns the number itself. So we can say something like, again, I can do times 3 times, let me remove this one, times 5, and then I just need to add something that guarantees that it's not a multiple of either of these things. So I could, for example, just add 1. And the only thing I need to do here is I actually need to copy that expression down here so that we see that the expected is that generated number, that transformed number. So that should actually work. And I still have 12 passing tests. Okay. So we now understand that at least there is a way where we can take any input value and transform it into a value that falls into a proper equivalence class. And this turns out this is a technique you can use for not only numbers but also for strings and all sorts of other interesting things. So often you can, at least. I'm not saying you always can, but this is a generalizable approach. You can often take some sort of input seed and transform it in such a way that it falls into a specific set of values that should provoke a particular outcome out of it. Right. So what's the problem here? Does anyone know the mistake that I made? Let's look at this one down here. What's the problem? It's okay. I mean, it's late in the evening. You don't have to feel stupid if you can't see it. Okay, so the problem is that I am systematically omitting certain values. I wasn't down here. The lowest one here, that one is fine. I can produce all the numbers that are multiples of 3 and 5 from any seed, because that's the definition of being a multiple of 3 or 5, is that you multiply a number by 3 and 5. Okay, sounds reasonable. The problem with doing this sort of thing where I add something is that now there are numbers that I can't reproduce. For example, if the input is 1 here, the resulting value will be 20. And if the input is 2, the resulting value will be 35. I can't arrive at 25 using any sort of seed. I can't arrive at 5 using any sort of seed. If I use 0 here, no, that's not true. Yeah, I can arrive at 5, but I can't arrive at 10. So if I use 0 as input, for example, the resulting will be 5. But if I use 1, the result will be 20. So I can't test with 10, for example. So what would happen if or someone else, some evil colleague of mine, would do something like this? So they would say, if number is 10, then blur. Else, and then we'll do the other thing. Okay? Now I can run this test, and it passes. It's not covered. So if you do code coverage analysis, you would see code coverage drop here. But if you don't do that, you might never notice that someone snuck in this sort of error into your program. This is not the correct implementation, but it passes all the tests that we wrote. So that's my error. That's my problem. On the other hand, we sort of understood that, I just banged on the keyboard to produce this number. It's a random number, as random as they get anyway. So if we know that we could use random numbers, why don't we? Why do we have to come up with those numbers? Why don't we just use random numbers? So that's the idea behind property-based testing. Why just throw a lot of random numbers at it and see what happens? We know that we can always, from the start of any random number, we know that we can arrive at something that deterministically drives the same behavior. So often when we talk about using random numbers for automated testing, that makes people uneasy, because they say, well, automated testing should be deterministic, and it's not going to be deterministic if we use random input. And the point here is that, yes, we use random input, but we transform or filter the random input into a way where the execution should also always be deterministic. And that's why it's important to understand what an equivalence class is. So we can do that with FsCheck. So this is where FsCheck comes in. And I know that I have 10 minutes or some sort of that left. So I can do, instead of having all this theory and stuff, I can just go property. And the only thing I need to do is I need to open that FsCheck module. This is the FsCheck XUnit module. This is what integrates FsCheck with XUnit.net, but you can also use it as a standalone library. But now I've just replaced all that theory and inline data with a property attribute. And what that's going to do, let me just try and run it and show you what it actually does. So if you remember before, it said 12 passed and 0 failed here. Now it says 10 passed and 0 failed. And that's because it's basically just counting all of those inline data and properties here. And I just removed 3 inline data, and then I added a property. So the property just counts as one test case from the perspective of the test runner. But actually what FsCheck itself says is, it says, okay, passed 100 tests. So what it actually did, it generated 100 random values, and it called that function, that test function, with those 100 random values. And it verified that in all of those 100 cases, there was no exception. There was no test failure. If there had been just one test failure, it would have stopped and say, well, this input value produces this test failure. So we can try to do that various times. So let's just do property for all of them. And that in itself is not going to help us, but it's going to put us closer to something that's going to be good. So I'll just do that for all 4 test functions. And I'll try to run the test again. And it's just going to pop up and says, okay, 4 passed, but we'll see each of those 4 is actually passing 100 tests. So I'm actually now running the test 400 times. It's still pretty fast, so that's okay. So for 400 randomly generated numbers, my code is passing. or my implementation is passing. But we still know that we actually don't have the correct implementation because I have this special case for the number 10. And the reason I'm not picking it up yet is because I still have this. I still have these transformations here. For example, in the bus case, I still have this transformation where I say, well, I take whatever random number that FsCheck generates for me, and then I do that sort of transformation. Now, there are two ways where we can arrive at numbers that fall into a particular equivalence class, and I've shown you one of them is doing a transformation. Taking any number and transforming that number into something that falls into the correct equivalence class. The other way that we can arrive at numbers that fall into a particular equivalence class is by doing filtering. So instead of saying, well, we'll just take those 100 randomly generated values that FsCheck provides for us and transform them into something that will always produce bus. We could also say, well, we'll take some random numbers and we'll throw away the ones that don't fall into that equivalence class. So we throw away all the numbers that are not multiples of 5. And now I'm getting into a double negation. That's difficult. I can't do that. Let's try to do it instead. So another thing FsCheck allows us to do is to do filtering. So let me start at the top here. So instead of doing this times 3 times 5 plus 1, what I could really say is I could provide a filter expression. That's a Boolean expression. And I could write it like this. So I could say something like, well, number modulo 3 must be different from 0. So this is F-sharp's different than operator. Usually you are used to exclamation point and then equal sign, but it's written like this in F-sharp. This means different from or not equal to. And it should also be the case that number modulo 5 should also be different from 0. Now this is a Boolean expression. This is my predicate, if you will. And then I can do this. I can provide a little custom operator, and that doesn't compile until I pull in FsCheck itself. So in F-sharp, you can define custom operators, just like you can. This is just a function. This is just a function. Instead of having a name with nice letters, it's just a function that has the name equal sign, greater than. Yeah, but it's a custom operator. It's just a function. So this is a function defined by FsCheck. And basically what it says is that, if this Boolean expression evaluates to true, the evaluation of the rest of the test should count as a test result. But if this Boolean expression evaluates to false, the evaluation of the rest of the test should not count as a test result. That's I deliberately say this in a strange way because you'll see why in just a moment. So the idea is that this acts as a filter. So the idea is that for the rest of this function, we should only care about what happens in this function if that condition actually holds. Okay. So if that's the case, I can remove all this transformation because now I'm doing filtering instead. Okay. So what happens when we run all the tests? We should expect that to succeed, right? But it fails. Okay. So this is a little bit funny here, but it actually says it's falsifiable by the number 0. But then we go, hey, but wait a minute. If we do 0 modulo 3, it's actually going to be 0. So this condition here evaluates to false. So why does it throw an exception? Well, it's because F-sharp is what we call eagerly evaluated, which means that it's still gonna evaluate the rest of the code. It's gonna run the rest of the code. So that's why I put it in that strange way before. The idea behind FsCheck is that if this evaluates to false, whatever happens down here, if it returns true or false or void or unit or whatever, it doesn't matter. But if it throws an exception, it throws an exception, and that always counts as a test failure. So there's a couple of ways we can deal with this. One of them is actually that FsCheck doesn't really necessarily want us to return units. So right now, if you remember, I talked about this. A normal test function is a function that returns unit or returns void, if you want to think about it in C# terms. But we can actually write our expressions as returning a Boolean expression. So now this is a Boolean expression itself. It's not a function that returns unit. It's actually the return value of this function is now a Boolean expression. So what that actually means is that FsCheck will look at what is the value that is being returned from the function. And then it's all going to pass. And the reason for that is that basically it's going to say, if this evaluates to false, I'm still going to run this, but I don't care what the result is, as long as it doesn't throw an exception. So let me pull this back that throws an exception, because that's actually what's happening. Now it throws an exception. Now we see the failure again. It says, well, it failed because there was an exception thrown. So we can make it lazily evaluated by doing this. We can just say lazy. This is more efficient, and this is why I'm showing you this, because otherwise I would be doing all those evaluations and then would be throwing away a lot of those results because they didn't count. But now I'm actually saying, well, in all the cases where that predicate doesn't hold true, I'm just not going to evaluate the rest. So that's even faster. So execution should be faster then. All right, so that passes all tests. So I can pretty much do the same with the rest. And I know I'm almost out of time, but I'm almost done always. Also, so in this case we can say, well, in this case the condition is that the modulo 3 operation should be 0, but the modulo 5 operation should be different from 0. So that's my FIS case, and I can do that, and that should hold. Yeah, 4 passed, 0 failed. Let's do this one and see if if anything surprising happens. So at least one of you are chuckling,
Yeah.
so you know what's going to happen now, right?
Yeah.
It's going to fail. Yes. Why does it fail? It says, yeah, you know what? This property is falsifiable because if we try with the number 10, we expected bus, but we got plur. Right. So now we actually do have coverage of this thing, and we need to remove that in order to pass all the tests. So that's
Another question.
yes.
If I use this property, it's not actually using random numbers because it would fail only in sometimes. So there is some.
So what most property-based testing frameworks do, including FsCheck, is that it has some values it always uses, and then it has some random numbers as well. So it will always try with some predefined values like 0 and 1 and -1, and I think it also does the max value and the minimum value of a 32-bit integer and so on. And then it also uses some random numbers. But yes, if I didn't do 10, if I had done, for example, if I picked a large number and done the if-then thing about that, it probably wouldn't have picked it up. Yes, but that's a good observation.
But if you would use max, wouldn't it overflow then when you have the transformation?
It might actually overflow when if we do the now right now we're doing filtering.
But
Yeah.
we had the transformation in there before.
Yes,
the filtering.
yes. So it might
It
actually
will
overflow.
overflow.
Yeah, it might actually overflow, or at least I think.
But wouldn't the transform is generated? It would automatically run in long.
Oh, you mean if it uses an int 64 instead?
Well, the type system would do it for you.
Yeah.
No, it's declared as an integer, so it would overflow, but I'm not sure that it would actually throw an exception. Let's try to experiment with that in the when we do the relaxation room afterwards and see what's actually happening. I'm not quite sure it does int max value. It might not do that. I might have misspoken there, but it does various random numbers at least. It may not do int max value. We'll need to figure that out. Let's figure that out afterwards. I just want to show you one more thing, and then we'll wrap it up and be done with it. Okay, because the last surprising thing is if we try to do the same thing down here, another quite a bit surprising thing happens. So we say, well, in this case, we want the modulo 3 and the modulo 5 operation to both be 0, and obviously we need to get rid of that transformation. Now we would expect this to succeed, but it fails for a different reason. So what it says here, if you can't read it in the back, it says arguments exhausted after 90 tests. So the reason for that is that, this is any Boolean expression you might think of. You could write a Boolean expression that looks like this. This is a Boolean expression. It says false. It's never going to pass. Okay? So FsCheck knows that you might write a Boolean expression here that will only pass in very rare conditions, or may never pass. And it doesn't want to generate numbers forever, because you want to discover those things. So actually what it does is, by default, it generates 1,000 random numbers, and as long as it can reach 100 valid numbers through your filter, it's going to be happy. But in this case, it couldn't. If you think about the bus case just up here, what we're doing is we're saying we're throwing away like 4 out of 5 numbers. Actually, we're throwing a little bit more away than 4 out of 5 numbers, because we're also throwing away the 5s that are multiples of 3. But we are throwing away approximately 4 out of 5 numbers. But it still means that by generating 500 random numbers, a little more, I can arrive at 100 numbers that can pass that predicate. The problem down here is that now we are throwing away 14 out of 15 randomly generated numbers. So even though it tries to generate 1,000 numbers, it doesn't reach 100 numbers. So we can tweak this in various ways, and this is just because I want to show you how property-based testing is always tweakable or customizable. So the first thing is kind of a hack, but you can say max fail, and you can say, well, let's just try to set it to 1,500. This is sort of on the edge of, sometimes it actually should fail. In this case, you will see it fails after 93 tests. If I run it again, it's probably now it's gonna pass. But basically, so this is just because I know that I'm gonna throw away approximately 14 out of 15 numbers, and if I do 1,500, on average, I should arrive at exactly 100. But that's just, probably gonna cut it a little bit too close. So maybe I can just leave a little margin for error in here, and just basically what I'm telling in here, so the wording here, the naming is kind of weird, but basically I'm saying, instead of having a limit of 1,000, the limit is now 2,000, and you should be able to arrive at 100 numbers that can pass that filter. But this is kind of a hack, because it doesn't really talk in the domain language of the test that we're trying to write. It's more like trying to fix FsCheck, if we will. So we can do something else. I can define a new type, if I could type. We could call that integers divisible by 3 and 5. So what I'm going to do here is I'm going to create a custom generator of integers that are multiples of 3 and 5. And I'm going to give it a static member, and we can call that int. It's not really important what the name is. And what I can do is, FsCheck comes with some random value generators built in, and these are called arbitraries. This is just the terminology of property-based testing. Such a random value generator is called an arbitrary. So it has default arbitraries. So I can say arb default, and I can say int 32. That gives me the default random number generator for 32-bit integers, and then I can pipe that. So this basically says, take the value of calling that function and then do something else with it. So I know this becomes a little bit F#-ish, but just so you can see the general gist of it. And then I can say map filter, and map filter is a function that takes both a mapper and a filter function in one. It's kind of a little funky, not that idiomatic, functional actually. But basically what we can say here, the x is going to be any integer. That's going to be the integer generated by that default integer generator. And we can say x times 3 times 5. Okay, because we know that will always give us a number that's a multiple of 3 and 5. And then we can say we need a predicate, some sort of filter. In this case, we can just say, well, it's just always going to, I know that this map will produce a number that's always going to be a multiple of 3 and 5. So I'm just going to use all of them. So this is a type. This is actually a static class, if anyone cares. And I do suspect that this is an emulation of Haskell's type classes, but this is kind of convention based. But what we can do is I can tell the property about the arbitraries that exist, and I can do that by passing in an array of types that implement custom arbitraries. So this is an array. This is an array, and I can say type of, and then the type that I just created, integers, something like that. I hope that compiles. So basically I'm saying to the property here now, there are custom arbitraries, there are custom random value generators available to you, and by convention it just looks at all the members that are here and it says, well, there's actually a thing that is an arbitrary of int, so I should use that to produce ints instead of the default arbitrary. So I could do that, and I have 4 passing tests or 400 passing tests, whichever way you want to look at it. And again, just if you don't believe me, I can comment this out, and we should have some failing tests. And as we can tell, it now says, this is falsifiable. If I use the number 0, it fails. So let me put this back. Right. Okay. And now it's passing again. Right. So let's just wrap this up, and then we'll have the real fun. The relaxation part. All right, so what I think is important here is to think about equivalence classes as sets. So in this case, I had some sets. I have a set of all the integers that are not divisible by 3 and 5. It's an infinitely large set, even though it's constrained, it's still infinitely large. But I like to think about equivalence classes or equivalence sets like, think about it as a, if you have, do you have here in Czechoslovakia, no, not Czechoslovakia, sorry. That just shows my age though, I grew up when it was called that, sorry. I'm sorry?
There are many Slovakians.
Yeah, we have nothing against those people, but it's just, no, anyway, but do you have TV lottos where, you have a lotto and then you have some guy that pulls balls out of a big ball of random numbers, yeah? So I kind of like to think about equivalence classes as, this is just a big ball of numbers where you can draw some numbers from it, but it doesn't matter exactly what the number is because they should all produce the same result. And then you have another ball of numbers that are all the numbers in the world that are divisible by 3, but not by 5. But it's not the same ball, it's 2 different balls. And you have a third and a fourth one. So all of these are in theory infinitely big. Of course, if you're working with 32-bit integers, they're just large, but not infinitely big. But in theory, they're infinitely big. And they have kind of interesting properties because if you do an intersection of these sets, it will be the empty set. There's no overlap. There's no intersection of any of those sets. They're disjoint. But on the other hand, if you do the union of those 4 sets, you will have the set of all integers. So these 4 sets together completely describe the domain of the problem. It's all the input values that could ever be applied to this particular problem divided into 4 sets. So whenever you want to have a test case, you just need to figure out, okay, what is the test case that I want to drive towards now, and you can just start pulling numbers out of that specific bowl. And as long as you pull from the same bowl of numbers, they are all equivalent. And that's why we call them equivalence classes or equivalence sets. So this is basically just, I hope this explains equivalence classes fairly well. I'm only just scratching the surface of what property-based testing is on the other hand. So if you want to learn more about that, then we can talk about that when we go and have, all the relaxation stuff, whatever that is going to. Is there going to be weed or something? But anyway, so next time, all right, I'll be coming back then. So you're welcome to ask me for the rest of the evening. Otherwise, you can contact me through those various means. And I hope that you got something out of this. And let's have a break. And thank you all for coming and bearing with me. Yeah. Oh yeah. So actually, I have some T-shirts to give. And I think you had a good question, so you definitely did. You want small or extra large? Small.
It's medium.
No, it's medium. I think that's what. So should I just throw the other one out and see who? Did anyone have a good comment? Or I can't remember. So I was so excited about this.
Whatever works for you.
Okay, catch. Oh. you know, given my skills in throwing, that was totally random. All right.
Okay, thank you, and let's
Let's move. Thank you.